Great. Thank you so much. My name is Daniel Dunbar. I'm a PhD candidate at Stevens Institute of Technology and also working at the Systems Engineering Research Center. I work with Dr. Mark Blackburn, and we have been doing a lot of work on ontology-aligned data and how to think about that in a digital engineering context. So I have a couple of papers there at the bottom right that describe our process and our approach. But here, this framework, the digital engineering framework for integration and interoperability, is a picture of our approach to ontology-aligned data. In digital engineering, you talk about the authoritative source of truth, and we view ontology-aligned data as a really good way of representing at least part of that authoritative source of truth. Now, I certainly ascribe to what Dr. Roquette said of you don't have one tool to rule them all. We are working on really complex projects with lots of different disciplines, and there's been decades of work developing different modeling tools for different problems, and they do their jobs really well. The problem of digital engineering is not creating a new tool to do all of that, but enabling connection of that. And so that's when I say ontology-aligned data as a portion of the authoritative source of truth. I want to acknowledge that ontologies are great for capturing data that connects the different tools. And so as far as an authoritative source of truth goes, the data in the ontology-aligned data is authoritative, but the authoritative source of truth is federated. It goes out to all of these other tools that have more of the complete fidelity of their particular models, so long as they agree with the few parameters that are shared with the ontology-aligned data. So with this, we have ontology-aligned data as our foundation. We have automated reasoning that comes with using a language like the OWL ontology language. And then we have to figure out ways to access that data. We have to have interfaces, and we have three different approaches to interfacing the ontology-aligned data. That first one is the mapping interface. The mapping interface is more of the traditional approach to interacting with ontologies and ontology-aligned data. It's taking from a tool and identifying in that tool how different parameters, different value properties align with the ontologies that you're working with. And so we have used SysML and system models to do a lot of that work, where we have tagged things with unique stereotypes that relate to classes in our ontologies. And that's how we program the ontology-aligned data. So it starts with the tool in question and then pulls the data in and maps it to the ontology. The specified model interface is notionally the opposite. We start with ontology-aligned data and we say what information is interesting to a particular use case, to a particular analysis model, to a particular visualization. What are we trying to do with this model, and what do we need to expose? And so that in that way, we actually specify a model of interest that we want to expose, and then go to the ontologies and pull out the specific data points that we want, and we can expose that via REST API as a JSON payload. And the way that we do that is in our SysML model. So you have a system under analysis, but we co-locate with that the system of analysis. And so the describing the interfaces and what information from the system under analysis we want to expose. We do that through the model interface specification diagram. And then the last interface that I'll talk about is the direct interface. And this gets us to more of core semantic web technologies, things like Sparkle queries, shackle constraints, lots of different ways of interacting directly with that. And I like to relate that to, you have a lot of data analysts that might be very familiar and comfortable with SQL, and they would prefer to access relational databases through SQL. They'll make the reports, they'll send them to people, but they really want direct access to that data. This direct interface gives us ways to use semantic web technologies to build tools that are directly interacting with the ontology-aligned data. And one of those that I'll go over briefly is the semantic system verification layer. And this is an approach that we've used for model verification, taking a look at models that are captured in ontology-aligned data and doing verification tasks based on a list of model requirements. So next slide, please. And this one has some animations you can just jump through. So here, this is a system of analysis is what it's abstract, but here, this is where I'm talking about co-locating the system of analysis with that we're trying to analyze. So there at the bottom, you have value properties associated with the system under analysis. This, of course, is a SysML parametric diagram. In the middle, you have intermediate analyses, different models. These are the interface specifications that I was talking about earlier that we are defining, and we are explicitly connecting with the system under analysis. And there at the top, you have analysis objectives. These are value properties within the SysML model, but these are what we're trying to get to. And this really builds off of Dr. Matt Chili's work with the integrated systems engineering decision methods on how to take a system under analysis, feed it through several different intermediate models to get to high-level analysis objectives. You can look at this and you can see that this is a graph. This is a directed graph that we could pull out and do a lot of different analyses on. But this is also how we are showing flow. So we can see things like sequence. Models 1 and 2 have to be run before model 3 because model 3 depends on the outputs of model 1 and 2 there. And by putting this into the SysML model that also contains your system under analysis, you can be very explicit and make sure that you understand how it interacts with the system you're trying to analyze. And so on the next slide, I'll talk through the system semantic verification layer. Next slide. And here, for the semantic verification layer, we wanted to look at different ways to approach verification. So some of these we've already talked about some today. So things like description logic reasoners, they're core to semantic web technologies. There's lots of research out there on how to use DL reasoners, what some of their limitations are, things like the open world assumption that Dr. Raquette talked about a lot. But there's some really interesting questions that we can talk through, and it uses formal mathematical logic. So we can build our ontology definitions to start to do some model verification. Now you have the open world assumption there, and so things that are really important from an engineering perspective, things like existence or minimum cardinality, are not answerable with a DL logic reasoner. And so we need additional prongs if we're going to do meaningful model verification. So prong 2 there is closed world constraint analysis. This is how we close the world, and we've used things like SHACL, the shapes constraint language, to take a closed world approach at the ontology aligned data. This is semantic web technology, but it allows us to close the world and look for things like existence. It also expands our model requirements to look for things like naming conventions. So it's not just definitional, but it's also things like a naming convention. And then the last prong brings in more general graph theory into the analysis. And so this builds on what an earlier presenter was talking about, but looking at things like is a subgraph of the ontology aligned data that was pulled with sequencing in mind. Is it directed graph? Is it acyclic? So if we think through that system of analysis on the last slide, if it's not an optimization analysis and you're not trying to do feedback, then you can say this needs to be directed and it needs to be acyclic. And we can start to do model verification on that system of analysis. And if we can show that, then we can also do things like automating the digital thread running through all 3 of those analysis models. We can do things like impact analysis. And so being able to look at model requirements and define them in an open world setting, in a closed world setting, and in a graph-based analysis setting gives us a broad suite of model requirements that we can start to check for automatically. And so with that, that's the end of my presentation. Thank you, and please reach out if you want to talk more about it.
Thank you so much.